civil engineering, we often make beams from things that are not rectangles. We already understand how to find second moment of area, resistance to bending, of a rectangular shape. The formula is 1/12 of BD cubed. But for a non-rectangular shape, we need a process. The first step in that process is to first of all find the centroid of the shape. Now, centroid is also a property of shape, just like area, volume, section modulus, and moment of inertia. And what it measures is the average location of all the elements on our cross section. It's akin to center of gravity or center of mass. It also will be the location through the depth of the beam where you have an equal amount of area above the line as below the line. And we have a formula for finding that. Now this formula looks a little unusual to us, so we're not going to freak out. It's y bar, which is how we pronounce that y with a dash over it, and we use that to denote centroid. And it's equal to the sum of all of the areas times all of the y bars divided by the sum of all of the areas. This formula makes no sense until you see the sums expanded. So what we do is we take our shape and we divide it into two shapes that we can control, shape 1 and shape 2. So in this case, the centroid will be located at the area of shape 1 times the location of the centroid for shape 1, plus the area of shape 2 times the location of the centroid of shape 2. You'll notice that I'm measuring the centroid from the top of the shape. I can measure it from any point in space. I've chosen the top. It doesn't matter where. The top is just a particularly handy one to use. And I divide all of that sum by the total area. For those of you who are statisticians, you'll recognize this as a weighted average. Each of the shapes gets a say as to where the centroid wants to live, but the bigger the shape, the more of a say it gets. And so this doesn't make a ton of sense until you see it actually done for a shape. So here it is for this concrete beam that has a T shape. Y bar is going to be area 1 times y bar 1, which is the area of shape number 1, the red shape here, is 12 by 3, and the location of its centroid is 1.5 inches from the top. And that's because it's a symmetric shape. I know where its centroid is. It's halfway down. Similarly for shape 2 is 8 inches by 3 inches, and the location of its centroid is halfway down the 8 inches. But because I'm measuring relative to the top, I have to count the 3 plus the 4 inches. In other words, I'm not measuring half the height of the object, I'm measuring the location of half the height of the object on my graph where all y bars are measured relative to the top of the shape. Divide that by the sum of the areas and I get 3.7 inches, which tells me if I replace the red line and the blue line here with this black line, that is the location of the centroid approximately for this shape. And what that location is the neutral axis. When that shape is a beam, this location, 3.7 inches from the top, is actually where the stress is going to be 0. You'll remember that from the last video. So now that I've found y bar, can I use that to find I? And the answer is yes. Now, I have a formula to find I. It looks very strange. You will never be expected to memorize this equation. It's pretty complex, and it's called the parallel axis theorem. Parallel axis theorem states that the I for any shape made of a bunch of shapes we do know the I for can be found by adding up all of the individual resistances to bending, that's these I shapes here, plus the area of those shapes times the distance of that shape's neutral axis to the neutral axis or centroid of the whole shape. This is a tricky concept. It basically says the further away from the neutral axis up here, this black line, all the stuff in part 1, shape 1 and shape 2 are, the better. In other words, if you can think of centroid as though it's an average location, resistance to bending is a little bit like standard deviation. How far on average is the stuff from the average? Okay, so if I fill this in, this is another formula that doesn't make a ton of sense until you see it used. This is the expansion. It means I need the I for shape 1 plus the area for shape 1 times the y bar of the whole shape minus the y bar of shape 1 squared, and so on for shape 2. So let's fill in those numbers. These are the numbers for shape number 1. and these are the numbers for shape number 2. And I've put in the red and blue line, which represent the y-bars of shape 1 and shape 2, where the black line represents y-bar for the overall shape. And when we solve this, we get our answer, which is 590.6 inches to the power of 4. I want you to notice that by far the largest contributor to that number are the areas times the distances squared, not the actual resistance to bending of the shapes themselves. This is an effect that you would see exacerbated if we did this calculation for a steel beam, where it would be all about how high up and how low down we put the top flanges and bottom flanges of our I-beam, and not so much about how good each of those individual pieces of steel were at resisting bending. This should be helpful for lecture next Wednesday, when we will be discussing concrete beams and how they act when they also have steel reinforcement.